So for this video, I'd like you to calculate this definite integral where the argument is the modulus of 1 minus 3x. So if you try it with pen and paper, and then you can come back and some different solutions and various comments will follow. So I will see you in a few minutes. Welcome back. Let's look at the solution. So if you want to integrate the modulus of a function, even a function as simple as this one, it's important to realize that there is no rule for integrating a modulus. So what we have to do is we have to think about what a modulus means. And the modulus of x is x if x is greater than or equal to 0, and it is minus x if x is less than 0. So to calculate this integral, we really have to face the question, when is 1 minus 3x positive and when is 1 minus 3x negative? And I think a picture helps us very much in such questions. So here I'm drawing the line, y is 1 minus 3x. It's a line with slope minus 3 and it crosses the y-axis at 1. And it crosses the x-axis at 1/3 because then that would vanish. So this is it drawn roughly to scale. So the modulus of 1 minus 3x is going to be the same as 1 minus 3x here, but for this region, from x being 1/3 to 2, it's going to be this multiplied by a minus sign. So it's very easy to draw. You just take this and you flip it about the x-axis. So what we're going to get is something that will look roughly like that. And this is, as well as I can draw it, this line flipped about the x-axis. And then to make it clear what I'm doing, I'm going to label this as follows. This is y is the modulus of 1 minus 3x. And for this line here, which we really use just to guide our eyes, I'm just going to use an eraser and get rid of it partly to show how we obtained it. So I will just remove some bits so we have a dotted line. And we can see that our function, the modulus of 1 minus 3x, is this line here. So now our interpretation of this integral is that it is this area plus this area here. So I can just draw that as follows. I'll just drop this line here, and then I will just colour in this triangle and this triangle. Just colour it in here and here. And we can use geometry just to calculate the integral. In a moment, on the next slide, I'm going to use the rules for calculus just to verify we get the same result. So this is going to be this area, half the base times the height because it's a triangle, plus this area, half a different base times a different height for that triangle. So therefore, the integral from 0 to 2 of the modulus of 1 minus 3x with respect to x is going to be, and it's going to be a half the base times the height, and the height of this triangle is 1 and the base is 1/3. So it is 1/3 times 1. Be very explicit, I'll write 1/3 times 1. And then for the second triangle, it's a half, and the height is 5, and the base is 1 plus 2/3, so that is 5/3. So it is, the base is 5/3, and that's multiplied by 5, that's the height. So I just made a comment using the area of a triangle is a half the base times the height. So therefore our integral from 0 to 2 modulus 1 minus 3x dx is going to be, well, a half is a common factor, so I'll pull it out, and a third is also a common factor, I'll pull it out, and a half times a third is a sixth. And that's multiplied by 1 plus, and then here we have 5 times 5, so that's 25. So this is 26 over 6. 2 is a common factor top and bottom, so it is 13 over 3. And this is positive, as would be expected, because our integrand is a modulus and it's always positive. We're integrating from 0 to 2, so we expect to get a positive result. And that is our answer for this integral. So on the next slide, what I'm going to do is I'm going to calculate and obtain the same result using the rules for calculus, but again, there is no substitute for thinking about how we define the modulus of the function, where we have to make these flips like this. We'll see that on the next slide. So on this slide, I want to calculate the integral again, but using the rules of calculus. But there is no way around looking at the modulus and thinking, when is its argument positive? And then the modulus is just the argument. And when is the argument negative? And then we have to put in a minus sign. 1 minus 3x is equal to 0 when x is 1/3. So therefore we see from this that the modulus of 1 minus 3x is 1 minus 3x if x is less than or equal to 1/3, because that is positive. And if x is greater than 1/3, then the modulus is 1 minus 3x multiplied by a minus sign. And if you multiply 1 minus 3x by a minus sign, you obtain 3x minus 1. So we can break up our integral into two integrals. An integral from 0 to 1/3 of 1 minus 3x with respect to x, plus an integral from 1/3 to 2 of 3x minus 1 with respect to x. And we talk about piecewise integration. So we are breaking up the range of integration into pieces, and we integrate over the separate pieces. And again, what we are doing is just like we were looking at a moment ago in the slides. We're saying that our integral looks something like this, and then there is something like this. And we have different rules for here and for here for what the integrand is. Now, both of these integrals are actually straightforward. You integrate 1, you get x. You integrate minus 3x, you have minus 3x squared over 2. Here you get 3x squared over 2, and here minus x. And you're integrating from 0 to 1/3 here, and from 1/3 to 2 here. So you just here put in the upper limit of 1/3, a third minus 3/2 times a third squared. And then you subtract this at the lower limit. When x is 0, these terms vanish. And then we add this at the upper limit. So you put in x is 2, so it is 3 over 2 times 2 squared, minus 2. Minus, open a bracket to write all of this out at the lower limit, and it's 3/2 times a third squared, minus 1/3. Close the brackets. And now we notice something interesting. Normally, and I'll talk about this a little more in the next slide, if you take a definite integral for some function which is defined with one rule, and you break it up in the middle, what you find is that the terms that you would define in the middle, say here a third and a third, would cancel. But this is not the case here because we have different rules for what the function is over this range and over this range. So you see here there is a third, and here it is minus a third, and they're going to add. We have this term with a minus sign, and we have exactly the same term, but with a minus sign again. So they will also add. They do not cancel. And I think that is actually really worth noting. So note the x is 1/3 contributions, the bits from those limits, do not cancel. And this is because although we are breaking up the integral here at 1/3, it is not one rule. There is this kink in the function and we have a different rule for it. Okay, so let's get back to the numbers. 1/3 minus, now when you square that, the 3 and the third will cancel, so you're going to get a half times the third, and that's a sixth. Minus 0, we're going to not worry about. 2 squared over 2 is 2, 2 3s are 6, minus 2. And then here, as mentioned a moment ago, we're going to get exactly the same thing as here. We get minus a sixth, the 3 and one of the 3's here cancels. You have 1 over 2 times 3 with a minus sign. And then minus minus is plus 1/3. So we've got 2 minus a sixth. Minus 2 sixths is minus 1/3, so that will cancel one of them. Let's say that. That means we're left with 1/3, a sixth, and a minus 2. 6 minus 2 is 4, and then we have plus a third. And 4 is 12/3 plus 1/3 is 13/3. So our result for the integral is 13/3. And that is exactly what we obtained from geometry on the previous slide. So it's exactly what we expected. So what we've seen on this slide is that if we use our understanding of how to write the modulus and we just calculate the integral, being careful, we get the correct answer, and we get this interesting effect that although we appear to have just broken up the integral, because there is a different rule here and here, these two terms do not cancel. I'll talk a little bit more about that on the next slide. So to complete this video, I'd like to just look at the claim that I just made on the previous slide, that if you have a function defined by a single rule, so y is some function of x, is not a modulus, and we want to integrate, say, from x is a to x is c, then we have the result that the integral of this function is going to be some antiderivative, an integral of the function little f, I'm calling it capital F of x, evaluated between c as the upper limit and a as the upper limit. And the standard rule for that is you evaluate this at x is c, and then you subtract this function at x is a. And we can always break this integral up as an integral from a to b, and then an integral from b to c. And in that way, we say that we're going to integrate from a to b, and then we add from b to c. And here, in exactly the same way as there, we have capital F evaluated at the upper limit minus capital F evaluated at the lower limit, plus capital F evaluated at the upper limit minus capital F evaluated at the lower limit. And if we look now, we see that we have f of b minus f of b, and we see therefore that they cancel. And we are left with f of c minus f of a, and that is exactly what we had there, and therefore we think that this is something that makes us happy. So that's a standard result that we have, but we saw on the previous slide that with a modulus function, because you are using different rules in different regions of the integral, this is not the case. You do not get that cancellation. To complete the video, I'd like to recommend to you that you take an exercise. So the modulus of 1 minus 3x is of course exactly the same as the modulus of 3x minus 1, because these two things are the same up to an overall minus sign, and the modulus function just makes them positive. So why don't you look at this and just repeat the solutions and see you get the same result. You're doing exactly the same thing. You can do it with geometry, you can do it by calculating the integrals, and everything will give you the same results. And I think that's a nice thing to do. And with that, I will stop this video.